Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode Problematic 3272. Find the count of good integer. This problem is based on recursion and also it is marked as hard, but don't worry, it will be easy to understand. It's just hard because of some corner cases and special conditions. Let's have a look on the problem statement. We are given two positive integers n and k, and they say that any integer acts as a k palindromic integer if it is following these two conditions. First one, it is palindrome. Second one, it is divisible by k. And what is a palindrome? If a number is something like this, if we read from it from starting, and if I read from it from the back side, it is the same. So 151, 1221, these are palindromic and divisible by k. So this number should be divisible by k. If we take the remainder with k, it should be 0. So that number will be called k palindromic. After that, they are saying an integer is good integer if its digits can be rearranged to form a k palindromic, right? So in this case, k palindromic is dependent on k. Let's say the value of k is 5, and if I just take this number 515, this 515 is palindrome, right? And 515 is modulus with k equal to 0. K is 5 here. So these two conditions are satisfied. It means this number is k palindromic. And now what is a good number? Good integer. Let's say if I just take 155. This 155 can be rearranged to this. And this number is k palindromic. So this good number we have to capture. So an integer is called good integer if the digits can be rearranged to form k palindromic. This is just an example given to us. And then return the count of good integer containing n digit, and this good number should be having n digits. In this case it is having 3 digits, so this good number is dependent on n and k palindromic, and k palindromic is dependent to k. They have also given a note that any integer must not have leading zeros. Okay, you can't just take a number. Let's say if n is equal to 3, you can't just take 011. This is not a good number. Also, the rearrangement you can't take like this. If let's say 1010 is our number, and you just do the arrangement and make it like this 0101. This is not a valid number. This is not a valid integer because it is having leading zeros. So avoid leading zeros. Okay, so this is our problem statement. Here the constraints are the length will go till 10 and the value of k will go till 9. Now I will explain it again to you with the help of an example. First of all, what is given to us? We are given two integers. N is equal to 3, the number of digits we want in our good integer, and k equal to 5. To check whether that number is k palindromic, we have to divide it with k. Apart from these two integers, we are also given these two definitions. First of all, any integer is k palindromic if it is satisfying these two conditions. First one, it is palindrome. Reading from starting and reading from back is same. So this is our first condition for k palindromic, and second condition, it is divisible by k. If both these conditions are satisfied, it is k palindromic. And what is our good integer? Any integer is good integer if that can be rearranged to form a k palindromic, right? If any integer of size n, let's say if n equal to 3, any integer of size n can be rearranged to form k palindromic, right? Then we are going to capture that integer. That integer is going to be our good integer. If I give you an example, let's say k equal to 5 and n equal to 4. So our good integer will definitely be of size 4, right? Because n value is 4. And if I just pick any of the 4 digit number, let's say I pick 2020. This 2020 I have picked, it is of size 4. So one condition is satisfy good integer. Second one is it should be rearranged to k palindromic. So let's say if I just try to rearrange and try to form a palindrome which is divisible by k. So in this case, it is, let's say if I just arrange it and I make it palindrome, it is becoming 2002. Rearrange. So this is palindrome But is it divisible by k? No, this is not divisible by k. So we are not going to capture it. If I just update the value of k to 2, if I update the value of k to 2, this is a palindrome and this is divisible by k as well. So if it is a 4-digit and its rearrangement is forming a k palindromic, then capture it. And all the integers that you have captured so far, which are good integer, just return that. Return the count of good integer. So we don't have to return the integer, we have to return the count of good integers. So here I hope that you have understood the problem statement completely, what we have to do and what can be our naive approach. So let's try to build and see how we can do it programmatically. First of all, we are given two integers, n equal to 3 and k equal to 5. So definitely our good integer will be of size 3. And then that good integer should be rearranged to any k palindromic. So to check this k palindromic condition, what I can do? First of all, my good integer will be of size having digit equal to 3. So if it is 3, it means I am definitely going to start from 100. There is no lower number than 100 of size 3. It means starting from 10 to the power 2 and going less than 10 to the power n. 10 to the power n minus 1 to less than 10 to the power n. So this is my range. This is my range, and in this range, what I can do, if I just do one iteration and see what is the current number. Let's say the current number is this. Then I can check all the rearrangement of that number. Right? Let's say the number is 221. 221. It is a 3-size number. Now I will be checking all the rearrangement of this number 221. This case can go to n factorial in the first case. Let's say the number is 1 2 3. I will try to see what are all the arrangement, what are all the possibilities, combinations of these digits. So these are the arrangements, and then I can check if this number is palindrome. This is my first condition, and second condition is if it is divisible by k. I can check the third condition. Then if this condition is satisfied, I can capture it. This is something given in the problem statement. They have asked us to do like this. So here in this case, if this is not going till n, this is going, let's say, till small n, number of digits. So this small n can be the number of digits, and for every number we can go n factorial, capital N factorial, to generate all the arrangements, and then we have to check the palindrome and capture it. So this time complexity is so high, and if we are doing it like this, going through all the iteration, all the numbers, it might be a very heavy operation, and there might be the possibility that a number, let's say 1221, can be arranged from multiple numbers. Let's say 1122, 2211, 1221 itself, 1212. For every number you are generating all the possibilities, and from all those possibilities you are capturing what are all the palindromes. So that is a very heavy operation. Instead, what is the alternative? We can already generate all the palindromes of n size. That will be our shortcut. So here what I have written in the notes: no need to go through all the numbers, generate arrangement and check palindrome. Right? Why there is no need to go to all the numbers? Because that is a very heavy duty operation. Instead, what we can do is we can directly generate palindrome, because we already have n till 10 size. So directly generate all the palindromes, because if we have the palindrome, if we have this palindrome number, I can easily get what are all the different numbers of 4 size which can give me this palindrome. Like, what are all the different numbers? These are like just shuffling of these digits. So there is no need to go through this iteration. So this is our brute force. You can try it by your own and see if it is getting submitted or not. For all the iteration, you just generate all the arrangements and check back for the palindrome. But instead we are going in a different approach, that's generating all the palindromes and see and later on we can see what are all the different combinations which can lead us to this palindrome. So now our problem statement has a sub problem which is generating all the palindrome of size k, right? Let's say I have generated all the palindromes. See, I have generated all the palindromes and those palindromes are in this list. So now what I have to do now, so those palindrome should be first position is that should be divisible by k. If that palindrome is divisible by k, then I am 100% sure that is a k palindrome. If that is a k palindrome, I need to figure out how many different 4-digit number can lead to this palindrome. All the numbers which are generated with the same set of digit as of this palindrome will lead to this palindrome. So this is something we will do. So for now, let's capture on this part that we are generating all the palindrome of size k. So here we are getting started with the generation of all the palindrome of size k. First of all, this n number can be of two types. It is even or odd. If it is odd, let's say n equal to 3. So it means we have to generate all the palindrome of size 3. It can be something like this: 1 1 1, 1 2 1, 1 3 1, 2 1 2, anything. So how we can generate? This we will have a look, and this can be even and this can be odd. Okay, for the generation of the palindrome, what I need to do is, first of all, I need to see what are all the different possibilities I can put at this index 0. At this index 0, what are all the different possibilities I can put? I can put from 1 to 9 digits. Why not 0? Because in the problem statement it is already given that we cannot have leading zeros. So 0 I need to avoid for the first position. Apart from that, after this, what are all the possibilities at this number? We can take anything from 0 to 9. But we are not going to keep on capturing the digits. See, palindrome is something from the starting and ending it is same. Then first element or the last element is same. Second element, second last element is same. Third element, third last element is same. Until we just capture the middle. So here in this case also we are going to do the same thing. First of all, what is the starting? This is the starting and this is the ending. And for the starting, if it is a starting, we can only pick digits from 1 to 9. So let's say I have picked 1. In that case, I also have to put 1 here, right? Because that is the only way to generate a palindrome. And after that, at the second position, see, after the first position, we can pick any digit from 0 to 9. We don't have to exclude 0. So you can pick anything. Let's say I picked 2, or let's say I pick 0, then it is fine. But after that, I don't have to cross it. Why? Because this is the middle. So we don't have to cross the middle. So we have to go to index 0, we have to go to index 1, but we don't have to go after that. At index 0, I can place anything from 1 to 9. At index 1, I can place anything from 0 to 9. Let's have a look on the even size as well. For the even size, this is the starting of the palindrome, this is the ending of the palindrome. At the starting, I can put any digit from 1 to 9. Let's say I have put 2. Then I also have to put 2 at the ending as well. So this is something I will do in one operation. And then when I'm going to the sub calls with index equal to 1, at this position I can place any digit from 0 to 9. Let's say at this position I place 0. So I have to place 0 as well on this position, because it should be like a mirror image, right? And after that, I'm not going further because the middle has arrived. So in the even case, we are having digit divided into two halves. In the odd case, the middle digit itself will behave like a mirror. And then what I have to do is, I just need to know how many indices I need to cover. Index 0 I have to cover, index 1 I have to cover. So in the case of n equal to 3, I will go to 0 and 1. At the case of n equal to 4, I will go to 0 and 1. So in this case, I'm going from, at 4, I'm going from, going less than n by 2. In this case, n is 3, I'm not going less than n by 2, less than n plus 1 by 2. Okay, if I just do n plus 1 by 2 here, it will also work fine. So to generate palindrome of size n, I need to start from index 0 and go till index less than n plus 1 by 2. So this is my range. This is my range that I have to fill. And apart from that, at the I equal to 0, I have the digits 1 to 9. At I equal to 1 onwards, I have digits from 0 to 9. So this is the main idea behind generation of all the palindromes. Now let's try to generate all the palindromes of size 3. Initially I is equal to 0, so we can pick any digit from 1 to 9, not 0. So I can pick 1, I can pick 2, I can pick 3, I can pick 4, I can pick 5, 6, 7, 8, I can pick 9. Anything I can pick. And now I am at index equal to 1. See, if it is a 3 size palindrome, I will start from 0 and I will go till n plus 1 by 2 exclusively. 0 is inclusively, that is exclusively. This is the range. So I have picked all of these digits. After that, at index 1, I can pick anything. Anything means starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So okay, these many things I can pick. After that I can go further, because for n equal to 3, it will be 3 plus 1 by 2, that is 2. So 0 is inclusive, 2 is exclusive. So only go till 1. After that, when I'm going till 2, what I can do? I can just capture the result. And how I'm generating the result? See, it is 3 digit. So when I'm picking 1, I am placing 1 at first and last. When I'm picking 0 at index 1, I'm placing it to index 1 and index 1 means second element. Second element from starting, second element from ending. So index 1 from starting, index 1 from ending will be the same element. Or formula, if I use the formula, what will the formula? So we have to put let's say our temporary of idx is equal to digit. Let's say digit is character. So temporary of n minus 1 minus idx. See, first one is 0, like last one is n minus 1, because this is n length palindrome. N minus 1 minus I. So place 1 at 0 and n minus 1. Place 1 is already there. Place 1 at this position. So this is how I'm going to generate my palindromes. Sorry, in this case it will be 0. See, initially I placed 1 on index 0 and index n minus 1, and then 1 was there. I placed 0 at index 1 and index n minus 1 minus 1. N is 3 minus 1 minus 1, which is 1 itself. So if I just go to the first call, I pick 1 and then just go to this call, let's say it will be something like this, 191. So this is also a palindrome. In this way we can generate all the palindromes. We are choosing length of n. We are choosing length of n, and at every moment I am choosing index. Index will go from 0 to n plus 1 by 2 exclusively. and every time I am placing the value at index I as well as index n minus 1 minus I. I will go from starting to here and I will be in this range. So here I will be able to generate all the palindromes, right? So once we have generated all the palindromes, I will just capture it, and later on I will see what I have to do. So this is the main part of this problem to understand. Solving should never be our purpose. We should always focus on the learnings. So this is something we have done. If I just try to write the formula, I'm writing a DFS function where n is the size of the palindrome, index is the starting index. We are starting from this, and apart from that, character array of size n. This is my temporary list. Okay, and whenever my index is reaching this n plus 1 by 2 or crossing the limit, it means I have filled the array. Let's say it is not returning anything. What is my base case? Let's say for 3 condition, I have filled 1 1 at index 0, and then I have filled 0 at index 1. After that, I'm not doing anything, so just return it and capture it. So base case will be if idx, let's just write the greater than equal to n plus 1 divided by 2. If this is the case, just capture it. Let's say capture is palindromes. Palindrome is a list of string is a palindrome. So palindrome dot add new, creating a string object with all the characters from my temporary list. Temporary list is a character of size n, and once you have captured it, just return from this call. If you have not captured it, you have some scope to add some element. You will be adding what element? This character element. And what is this character? Character is like index, not index. See, currently we are at index, and at index we have to see what are all the possibilities we can put, and those possibilities are from 0 to 9, and at the first case it is 1 to 9. So I have to write a for loop. For loop I equal to 0, I less than equal to 9, I plus plus. And what is the character? Character is I plus 0. This is typecast to character. I plus 0. You just assume that it is the right character. So okay, if this character is there, my temporary list at index idx, I need to put that character. At index n minus 1 minus idx, I need to put that character. And then the solution call. Solution call will be n and idx and this temporary list I am passing. See, if I just zoom out, this is my code to generate all the palindromes of size n. All the palindromes of size n. And what is the time complexity? Let's say I am generating palindrome of size n. In that case, I am only filling half the digits, and at every step we are having 10 possibilities. So 10 possibilities raised to power n by 2. So this is the time complexity to generate all the palindromes. I have generated all the palindromes, and then I'm going to capture all the palindromes in a list. Okay, so let's say this list is having all the palindromes. List is having all the palindromes, and I'm iterating over this list from index 0 to index size minus 1. I'm picking one palindrome. Let's say P palindrome I have picked. First of all, I will see that whether this palindrome is K palindrome. To convert it to K palindrome, I will just have a look whether this number as an integer modulus K is equal to 0. Then this is K palindrome. Now I have K palindrome, and I need to see how many times this K palindrome is being generated, right? From how many digits of size 4. How I can check? Let's say this is 1 2 2 1. This 1221 can be generated from 4 digits of multiple numbers. Let's say 1122, 2211, 1212, and so on. So from this I need to know how many digits are there, and that is like these digits are just combination of these numbers. So whatever is the number of digits into this n factorial divided by, see, permutations are there. These are like shuffling arrangement. So permutations mean n factorial divided by n, these are 4 digits, so n minus n factorial, and divided by number of digits which are repeating. So 2 is coming 2 times, 2 factorial, 1 is coming 2 times, so that is 2 factorial, and n is 4. So 4 factorial divided by 2 factorial divided by 2 factorial will be the number of digits that can lead to this K palindromic. These are the number of digits which can lead to this K palindromic, because ultimately we need to capture that number. Whether that number is good number or not number, if the shuffling rearrangement, if the rearrangement is leading to K palindromic, it means this K palindromic is the shuffling of this number. So we have done in the opposite way. So these are the number of good integers. Okay, but there is one special case as well. Let's say if it is 1001. So this 1001 can also be arranged from 1100, 1010, right? In this case, we should not take the permutation where this number is starting from 0. So let's say first of all we have taken the possibility of all the numbers with these digits. What are all the numbers? 4 factorial divided by 2 factorial divided by 2 factorial minus the number which are starting from 0. It means starting from 0, 3 number can be anything. Starting from 0 is, we have fixed 0. Now we have 3 numbers, and these 3 numbers are 0, 1, 1. So minus 3 factorial divided by 2 factorial. So this formula is going to give me all the numbers which numbers which can be rearranged to K palindromic, right? Yeah, this is something we have to capture, and there is another last case that we also need to take care of. The last special case is something, let's say 2 palindroms are there. We generated 2 palindroms. So when I just came to this palindrome, I captured all the numbers who generated this palindrome, right? And then after some time, when I will just come to this palindrome 1, I have captured palindrome 1. At the time of palindrome 1, I have captured all the good integers which are rearranged to this palindrome. At the time of palindrome 2, because I generated all the palindromes, at the time of palindrome 2, I am going to capture the same set of numbers, right? Why? Because 1 is 2 times, 2 is 1 time, 2 is 2 times, 2 is 2 times, 1 is 2 times. So this is also going to give me the same set of integers. So these set of integers will be counted twice, right? So we have to build some kind of scenario that we are not able to count these numbers twice. These number 1122, 2211, 1221, 12, like 2121, anything. So this is also going to have the same set of element. So here, what is the frequency set of any palindrome? I need to have a visited set for that, right? So that's why this problem is hard, because there are so many conditions, so many corner cases. That first one corner case is that the number should not be having leading 0. Another corner case is that this palindrome can be generated from the same set of elements. Same number of digits can generate different palindromes. Let's say this palindrome 1, palindrome 2. These we should consider as a one unit. So here in this case, I need to have a set where I am going to mark it as a visited. And how I can mark it visited? The frequency set, I need to convert it as a key, and I can mark it visited. Okay, so let's say 1 is coming 2 times and 2 is coming 2 times, right? So from this, 1 is coming 2 times, 2 is coming 2 times, these two keys will be same, so I'm going to skip capturing answer from this. So that's all we have to do. So first of all, generating all the palindromes and then iterating over all the palindrome and see what are all the palindrome which are k palindromic. It means divisible by k. Now we have a certain set of palindromes. Then we need to process that palindrome to see from how many numbers I can get that palindrome and just capture those numbers. And make sure from those numbers you are not maintaining leading zeros. After that, mark the frequency set of that palindrome visited, so that the same frequency set palindrome does not appear again. That is something we have to do. Like here, if I just write the steps, generate palindromes. Generating palindromes is order of 10 to the power n divided by 2. Generate order of n divided by 2, and here in this case, after that, so once we have generated all the palindromes, after that I will be iterating over all the palindrome and see if it is modulus with k equal to 0. And other thing is that from that palindrome p, I will see how many number I can generate, and that will be utilizing some formulas like factorials and all. So these factorials and all you can calculate manually, and you can also, because these n number can be from 1 to 10, so there is a limited set of numbers, so you can memorize that as well, but I have not memorized it in my code, so you can use it directly. So n factorial is going to be the case, but in this case it is till 10, so the complexity will be like this overall from my approach. Okay, now let me show you the code. Now let's have a look at the code. Here first of all, I'm capturing all the palindromes in this palindromes list. So I have generated all the palindromes of size n. After that, I'm iterating over all the palindromes. First step is checking that whether that palindrome is k palindromic or not. Now palindrome is of n size, it is a k palindromic, and now I just need to capture the integer which are leading to that palindrome, which can be rearranged to that palindrome. So for that, I'm just capturing the frequency of that palindrome. Once I have captured the frequency, I am also marking it visited as well, so that it is not processed again. So frequency is captured. Now just get to know how many different integers are leading to this number. So that is this function, count permutations. Count permutations, all the numbers. If I am having 0, then this is the formula, n factorial divided by all the repeated number, r factorials. If it is having 0, then we have to reduce the n minus 1 factorial divided by remaining frequencies as well. So this is the same formula that I have discussed in the approach. So this formula is going to give me all the numbers, and now I have the numbers. These numbers are leading to a k palindromic number of size k. That is counted to my total. So here this compute permutation is dependent on this factorial function. So this factorial function is nothing, just a normal factorial function. You can also do it. And generation of palindrome is more important than to me. And building signature, see, this is nothing, like whatever is the frequency, I'm going to capture it in the set. So it's totally up to you how you can capture this frequency. You want to like create a string of anything, like I just created a string appended with x and underscore. Now let's come to our main function, which is the palindrome, where we are using the recursion. So here the palindrome is of size n. It means our index will go from 0 to n by 2, n plus 1 by 2, less than n plus 1 by 2. So if it is crossing the limit, it means my palindrome is already filled, just capture it. Otherwise, fill the digits. At the first time, you fill the digit which is 0 to 9. It is 0 to 9, but for the first position only, just skip the 0. if I equal to 0, it means I equal to 0 for idx equal to 0. It means we are filling it for the first time and we are trying to fill 0. So in that case, just continue. Otherwise, just capture this character and move further. So yeah, that's all in the problem. And I'm just going to attach the code in the description below. You can have a look. Is the clean code without any fancy logic. Thank you guys. Bye bye. I hope you understood the approach. In case you get any doubt, you can comment down below or discuss in the Discord community. Bye bye.